Alright, video 2. So let's take a look now at a graphical representation of what we've got going on here with partial derivatives. So determine the signs of the partial derivatives for the function f whose graph is shown. So see here, you can see how we have this surface, and I'm not sure if you can see it real well, but right there is the point in question. So that is the point 1, 2 on the graph, it looks like. And what we're asking in A is, what is the derivative or partial derivative with respect to x here? So we want to know basically, how is the z value changing as x changes if we hold y constant? And so graphically, let's look at that. How is the z value changing? Z is the height here. You can see here's the z-axis. If we only change x, that means we're holding y constant. So here's your y-axis right here. We're going to hold this y value constant. So this is the x direction here. How is this x value changing? That is a really, really bad sketch. Oh, new photos have arrived. Wonderful. Thank you. Um, let's see if I can do this a little bit easier with a thinner line. So how is this changing? And it appears along that line right there where we're holding y constant, it appears right here that this is sloping upward. Looks like it's curving upward. So we're looking at f of x, again holding y constant at 2, and I guess that's supposed to be at 2, um, at the point where x is 1. So how is this slope changing as x increases? It looks like the z value is going up, it's getting higher. So we would expect that sign is greater than 0. And let's take a look at the partial of f sub y. That means we're going to hold x constant. We want to know how the y value is changing. So let me change colors here. So this time we're holding x constant, so we're talking about the y change, which looks like it's doing something like this, and you can kind of see how this thing is curving, sloping. It looks to be down. It's coming down this hill kind of off the surface here. So as y increases, as y is getting bigger here, it looks like the z value is dropping. So the partial derivative of the function with respect to y only looks like it is negative. The thing is sloping down. Okay, hopefully that makes more sense than what I tried to do in the first video. This is a much better visual. I think you can see that a little bit better. All right, now we're going to move into the algebra of this. So example 3. If our function of xy, you can think of that as z if you want to, is 16 minus 4x squared minus y squared. We want to find the partial of x at 1, 2, and we want to find the partial of y at 1, 2, and interpret these numbers as slopes. And if we can, illustrate with either a hand-drawn sketch or computer sketch. We're going to try and do this thing by hand. My resources are a little bit more limited here at home. So, um, okay, so let's take a look. If, let's see, if x equals 0 and y equals 0 on this thing, we simply get z equals 16, right? So let's put that over here. If x equals y equals 0, then what we get is z equals 16. If we were to let z equal 0, if this thing over here, again, remember that this is like having z, if we let z equal 0, then what we have is 16 minus 4x squared minus 4y squared, or equals 0. Or if we add these two things to the right, we get 16 equals 4x squared minus, I'm sorry, plus 4y squared Somehow I've gone ahead and added a y in here, I mean a 4 in front of the y. I'm not sure how or why I did that. That should not be there. Alright, that's better. Um, Equals 0. Nope, not equals 0. Lost my train of thought. Gone. And then if you divide both sides here by 16, what you end up with 1 equals 4 over 16 is a fourth, so x squared over 4, and then plus y squared um, over 16, which is the shape of an ellipse. And you probably could have told by looking at this thing, the z equals 16 minus 4x squared minus 4y squared, 2 squareds, 1 non-squared. What you have is an elliptic paraboloid. So let's go ahead and take a look at a sketch of what that would look like. So an elliptic paraboloid. What it appears is in the x direction it's going to go out about 2 units, and in the y direction it's going to go out about 4 units in both directions. So let's see how this works. If it goes out 2 units in the x direction, 4 units in the y direction, it's 2 units in the x direction here, 4 units in the y direction there, something like that for your base. Not the best oval, not the easiest thing for me to draw on here. Um, so there's your ellipse, and then the paraboloid part of it, it's going to go up. It's supposed to reach, well, it's supposed to reach z equals 16, which is, way up here somewhere. It'll have this general shape to it in that direction, and then in the y direction, something like this. I almost made it. So not the best. It basically looks like an upside down bowl. But there's your elliptic paraboloid. It's kind of what it looks like there. So let's take a look. Oh, and let's do this in green. Um, the point we're interested in is the point 1, 2. So that's out 1 this way, 2 over this way. What we're looking for is where this thing hits, which is probably someplace right up here towards the top of this thing. And it's going to hit on the surface, on the outside of this surface here somewhere. So let's go ahead and take a look at these partial derivatives, and we'll see if any of that makes sense. So we're going to have the partial derivative of xy with respect to x. So the partial of x. Well, the partial of x, what that's saying is we're going to take the derivative of this thing as if x was the only variable in here. We're going to treat y like it's a constant. 16 we know is a constant, but we're going to treat y like it's a constant. And we know that the derivative of any constant is 0. So really the partial of x, when we're holding y as a constant, is going to be 0 minus 8x minus 0, which is just going to be negative 8x. And if I want the partial at the point 1, 2, that says take the partial derivative with respect to x and then plug in 1 for x, 2 for y. Well, I only have an x to plug it into, so what we get is negative 8. And then it also wants me to find the partial with respect to y. So that was the partial with respect to x. Now let's do the partial with respect to y right here. So the partial with respect to y of xy is now looking at this thing. Now we're going to hold x as a constant and only take the derivative of y. So 16, negative 4x squared, those are all constants in this case, so that's 0. So the only thing I'm taking the derivative of is right here, which is negative 2y. And then, of course, I want f partial of y at 1, 2. That means I'm going to plug 1 in for x, 2 in for y. Well, here I don't have any x's, but I do have a 2 to plug it into, so I get a negative 4. All right, so now let's come back to the graph over here and see if this makes sense. Well, what this is saying is the partial with respect to x, as x starts to increase, so x goes out this direction right here, what is the what is the z value doing? Well, as x goes this way, this thing is coming down. There's no question about that. This thing is sloping down the outside of this elliptic paraboloid. And that makes sense. It's got a negative 8 slope. So for every change of 1 in the x direction, the z value is dropping by 10. And that makes sense. Look how steep this thing comes down. For every change of 1 in the x direction, the z value is dropping by 8. If you really think about it, it makes sense. If I start at 0 and I go out 1, I'm going to be at negative 8. If I go out 1 more, I'm at 0. Subtracting 8 each time is going to get me down to the bottom here. And then the partial with respect to y, so as y increases, so as y goes this way, right here, what's the z value doing? Well, again, it's coming down the outside of this thing in this direction, and it's changing by 4. So as y increases by 1, z decreases by 4, z drops by 4. And again, that should make sense. If you start at 16 way up here and you go out 1, 2, 3, 4 units and you're supposed to drop by 4 every 1 unit moved, that's going to drop you by 16. It would end up right down here at the bottom. So it actually does kind of make some sense there. So it's telling you how is the z value changing when the x is changing and y is held constant. Or here, how is the z value changing when y is changing and x is held constant. That's the idea of the partial derivative. Doing them is actually very easy. It's relatively simple, especially because you get to hold the other one constant. Let's do some more examples. Find the first partial derivatives of the function f of xy equals 3x minus 2y to the fourth. So the first partial derivatives are just f of x and f of y. Partial of x is going to be, well, what's the derivative of this thing with respect to x only? Remember, y is constant, so the derivative of this is 3. And if y is constant, that whole thing is a constant, it's 0. So the partial with respect to x is 3. Partial with respect to y. Now the 3x is constant, so just take the derivative of this part, because the constant goes to 0, and that's going to be, bring the 4 down, it's going to be negative 8y. Okay, pretty simple to do a partial derivative for the most part. Find the first partial derivatives of z equals x e to the 3y. So we want to take, in this case they gave us z, so we're going to use the notation of dz, and we want to do it with respect to x first. And we want to do dz, partial of z, with respect to y. So let's do x first. If we take the derivative of this with respect to x, well, this whole e to the 3y is a constant now because we treat y as a constant. So that's really like having a coefficient in front of x. And the derivative, if it was just 5x, would be 5. So this is just going to be e to the 3y. Now we're going to take the partial with respect to y. Remember, x is now a constant, so it's just like having a coefficient out in front of the e. And hopefully you guys remember that the derivative of e is itself, but then you multiply it by the derivative of the exponent. So really what we're going to get is x e to the 3y times 3. And that's your partial with respect to y. All right, moving on. See, I told you these would go a little bit quicker now. Find the first partial derivative of the function f of rs when r times natural log of r squared plus s squared. Okay, so first partial with respect to r. Now, this is a little bit different. Now, I've got r here and I've got r in here, so we've got a product rule. Okay, that's really the first function. That's the second function right there. So we are going to have to do this as a product rule. So it looks like the derivative of the first, which is 1, times the second, natural log of r squared plus s squared, plus The derivative of the second, remember the derivative of a natural log is 1 over the argument times the derivative of the argument, but remember s is constant now, so it's just multiplied by 2r. And then you got to multiply it by the first. Don't forget that part. So this is the derivative of the second right here, and then times the first. So kind of cleaning that up there, it's going to be the natural log of r squared plus s squared plus, that's going to be, what, 2r squared over r squared plus s squared. And now we want to do the partial with respect to s. Okay, no product rule now because the s is only located within the natural log, so this r is like a constant out in the front of the natural log, so it just kind of stays there. So this will be r times the derivative of the natural log, 1 over r squared plus s squared times the derivative of the argument, in this case, which is just the derivative of the s squared, so that's 2s. So cleaning that one up, it looks like we would get 2rs over r squared plus s squared. Alright, hopefully not too bad. Again, I do believe that once you get used to this, the derivative portion is pretty easy to do. Alright, find the first partial derivatives of this function. So now I got 3 different independent variables with a dependent variable of w. So now I have 3 partials to do. Alright, so let's see. We're going to have the partial of w with respect to x, the partial of w with respect to y, and the partial of w with respect to z. So let's see, the partial of w with respect to x first. Each one of these things is going to be a natural log, so it's 1 over x plus 2y plus 3z times the derivative with respect to x of the argument when that's just 1, so that's finished. The partial of w with respect to y, again y is in the argument, so it is going to be the 1 over x plus 2y plus 3z multiplied by the derivative here of the argument, but again y is the only variable, so that's going to be multiplied by 2. So let's get rid of that, and that's just going to be multiplied by 2, so we got 2 on top. And then the derivative of w with respect to z only, same idea, it's going to be 1 over the argument times the derivative of the argument. The derivative here is 3 of the z part, so there you go. There are your 3 partial derivatives because you had 3 independent variables. Alright, so the last one here says find the partial derivatives of the function, so I guess it wants us to find all 3, and then specifically it says find f of z at the point 3, 2, 1. Alright, so let's take a look at the partials. So we're going to have an f sub x. Okay, so one thing you want to realize is this is the same thing. Remember, x is the only variable, so this is the same thing as saying x times 1 over y plus z. So this is like a constant. This is a coefficient. So x times this, the derivative of that is just 1 over y plus z. Partial of y. Now y is in the denominator, so we can't really do the same thing. But what we could do is we could rewrite this function. Instead of doing it like that, we could also rewrite this as x times y plus z to the negative 1. And remember, x is a constant in this case, so we're going to bring that negative 1 out and multiply it by the x, and then reduce the power by 1, and then multiply it by the derivative of the inside, but the derivative of y is 1. So we should get negative x y plus z to the negative 2 times the derivative of y, which is 1. So we end up with negative x over y plus z quantity squared. And then partial of z, exactly the same concept that we just did here. As a matter of fact, it's going to be exactly the same derivative. Um, so it's going to be negative x y plus z to the negative 2 times the derivative, times the derivative of the z, which is 1. So we end up with negative x over y plus z quantity squared. And specifically, I am looking for, it told me to find the partial of z at the point 3, 2, 1. So we're just going to plug 3 in for x, 2 in for y, 1 in for z, and we are going to get negative 3 over 3 squared 9, so we're going to get negative 1/3. And that is your partial of z at the point 3, 2, 1. All right. See how we're doing. We're at 21 minutes, so I think what I'm going to do is, yeah, I'm going to stop the video here and come back with a third video, and that will be the finisher.